The modern Android system on a chip is an integrated environment engineered to handle a continuous, extreme computational load. Standard mobile applications now compete with persistent on-device intelligence, requiring complex models like Gemini to run continuously in the background. Alongside these AI models, we see the rise of safety-critical, persistent automotive human-machine interfaces operating at the dashboard level. This image shows the juxtaposition of the standard Android OS acting as the foundation for a heavy, embedded 3D automotive system check built by tools like Kanzi. Integrating these subsystems required deep embedding directly into Android's hardware abstraction layer. This creates a direct resource conflict. These continuous workloads require a massive memory footprint, yet Android operates on strict hardware constraints. Android's memory philosophy is built on a single premise: free memory is wasted memory. The OS intentionally fills available RAM with cached processes to ensure the user can switch between apps instantaneously. To maintain stability in this ecosystem, systems engineers must deconstruct the mechanics of Android's memory reclamation lifecycle. Architecting for these environments without understanding this lifecycle leads to unpredictable process termination. This schematic outlines the three memory domains on a device: the slow, persistent storage, the fast, limited RAM, and a specialized partition called ZRAM. Because frequent writing to flash storage causes physical wear, ZRAM acts as a compressed swap space kept entirely within the RAM. The operating system manages this space using a specific base unit, the 4 kilobyte page. The system differentiates these pages based on their relationship to the storage drive. Clean pages are unmodified, exact copies of files that already exist in storage. Dirty pages hold data that has been modified by an active application. These represent a state that exists nowhere else. Finally, anonymous pages hold memory dynamically allocated by the system, with no backing file on the storage drive. Both dirty and anonymous pages are vulnerable. Because they represent unsaved data, the system cannot simply wipe them to clear space. When RAM fills up, the state of these pages determines exactly how the system will attempt to reclaim that memory. When memory usage crosses a predetermined low free memory threshold, it triggers a kernel-level reaction. This threshold is the mathematical trigger for the kernel swap daemon, or kswapd. The daemon's primary function is aggressively converting used memory back into free memory. Its first move is targeting and instantly deleting clean pages. This is a safe operation because identical copies of these files remain on the flash storage. This relies on a concept called demand paging. If a process later needs one of those deleted pages, the system simply stops and recopies it from the storage drive back into RAM. But kswapd must still address the undeletable, dirty, and anonymous pages. Since these modified pages cannot be deleted, they are forcibly routed into the ZRAM partition. Here, a compression algorithm shrinks the data, artificially expanding the device's total available memory. This comes with a performance cost. If the CPU needs that data, it must pay a decompression tax, spending cycles to unpack the page before moving it back into main RAM. kswapd continues these operations until the high free memory threshold is restored. This balancing act acts as a high-speed buffer, buying the system critical time before a much more permanent and drastic solution is required. If the swap daemon cannot reclaim space fast enough, the system begins to fail under the pressure of the workload. In this scenario, the kernel deploys its last resort, the low memory killer, or LMK. The LMK does not compress or move pages. It terminates entire processes to reclaim their footprint instantly. To decide which process to end, the LMK uses a prioritized kill list called the adjust score. Background apps are at the top of the list. They are killed first, starting with the highest score. If space is still needed, non-foreground apps that are perceptible to the user, like a background music service, are killed next. The bottom tiers are heavily protected, containing foreground apps, persistent services like telephony, and native system processes. The foreground app is shielded because its termination is experienced by the user as an application crash. Stability requires architecting processes to sit as low on this score table as structurally possible. To stay clear of the low memory killer, engineers must be able to accurately measure an application's physical memory footprint. This is complicated by shared memory pages, which are common when multiple apps utilize the same native Android libraries. The most common metric used is resident set size, or RSS. RSS is flawed for system-level planning because it double counts those shared pages for every process using them. On the other hand, unique set size, or USS, is incomplete, as it ignores shared pages entirely. The most accurate metric for system survival is proportional set size, or PSS. PSS mathematically distributes the cost of shared pages across all processes utilizing them, giving a precise account of the total hardware load. Workloads like Gemini and Kanzi HMI must monitor their PSS strictly to coexist within Android system boundaries. By mastering page states, compression, and PSS metrics, engineers can repurpose an operating system optimized for mobile phones into a stable platform for high-performance embedded systems.